Okay, hello everyone. Today we'll just do some examples of induction. So let us remember what the principle of mathematical induction is. So let S be a subset of the natural numbers n such that 1 belongs to S, and if n belongs to S, then n plus 1 will also belong to S. Then S is the entire set of natural numbers. In another way we could phrase it, so if Pn is a proposition or a statement such that P1 is true, this case we call the base case, and that if Pn is true, then Pn plus 1 is true. This is we call the induction step. Then Pn is true for all n in n. Let us start with a small example. Show that for every n in n, the sum of the integers from 1 up to n is equal to the n times n plus 1 over 2. So first, the base case. Check that P1 is true. Well, let's call this statement Pn. What does P1 say? Let us write what P1 is. P1, it says that 1 is equal to 1 times 1 plus 1 over 2. Well, P1 is true, obviously, since 1 is equal to 1. Now the induction step. Basically, suppose that Pn is true. For some n. We need to show now what is Pn plus 1? Pn plus 1. So we look at this statement, we look at Pn, and wherever we have n, we replace it by n plus 1. So Pn plus 1 is 1 plus 2 plus, well, I have n here, I get n plus 1. So really, it's the sum of the integers from 1 to n plus 1 is equal to. So here I have n, I replace it by n plus 1. And there, I replace the n by n plus 1. So the n plus 1 will become an n plus 2. So n plus 1 over 2, which I can write as n plus 2. Well, I mean, this is just n plus 1 times n plus 2 over 2. Now, in order to show this, I need to use the induction hypothesis. The goal is always to use the fact that Pn is true. Now, let me write this. The left-hand side is equal to n plus 1. Now, notice this is just equal to the sum of the integers to n plus 1. Well, before n plus 1, we have n. Now, let me rewrite this in a better way. If I combine the terms in such a way where I can isolate or where I can see that Pn is being used, then I might be on the right track, because by the induction hypothesis, I know that this term is equal to n times n plus 1 over 2. This is by assuming that Pn is true. Now, plus n plus 1. Now it's just a matter of factoring and regrouping, basically. Let me factor n plus 1 out, so it's n plus 1 times n over 2, right, plus 1. Let's put everything on a common denominator, n plus 1 times n plus 2 over 2. Hence, What is Pn plus 1? Pn plus 1 is that the sum from 1 up to n plus 1, the sum of the integers from 1 up to n plus 1, is equal to n plus 1 times n plus 2 over 2. Wait a minute. This is what I have here. So hence Pn plus 1 is true. Hence, by induction, Pn is true for all n. Well, what is Pn? It's 1 up to n is equal to n plus 1 over 2 for all n in n. Okay, now let us do an example. Another example, slightly more complicated, but not that much. So show that for every natural number n, the sum 1 cubed plus 2 cubed plus up to n cubed is equal to n squared times n plus 1 squared over 4. Now let me call this statement Pn, and let's see what P1 is about. Base case, P1 states that, well, on the left-hand side I will have 1, on the right-hand side I'll have 1 squared times 1 plus 1 squared over 4. Well, of course, P1 is true, since let's say 1 squared times 1 plus 1 squared over 4 just equal 4 over 4 is equal to 1. Now we do the induction step. Well, what does the induction step say? It says, or it consists of assuming that Pn is true for some n in n. Assume that Pn is true for some n in n. We'll show that Pn plus 1 is true. Well, what is Pn plus 1? Let us write this down. Remember, I take Pn, I replace wherever I have an n, I replace it by n plus 1. Wherever I have an n, I replace it by n plus 1. So it's 1 cubed plus 2 cubed. Well, I have an n here, so it gets n plus 1 cubed. What is it equal? So the n squared becomes n plus 1 squared, and the n plus 1 becomes n plus 2. Over 4. Let us do this. So 1 cubed plus 2 cubed plus n plus 1 cubed. Now remember, the goal is to be able to use the induction hypothesis. So I need to let the induction hypothesis appear at some step, basically. Oh, wait a minute. Oops. Isn't this my induction hypothesis? Since Pn is true, after grouping the terms in such a way, what do I get? I get that 1 cubed plus 2 cubed plus until n cubed is equal to n squared. Well, let me write this down in yellow because I'm using the induction hypothesis. Over 4 plus n plus 1 cubed. Great. Now let me factor in n plus 1 squared. This is a common factor here. N plus 1 squared. This is n squared over 4 plus n plus 1. I need to get to n squared to n plus 1 squared times n plus 2 squared over 4. Let me put this in a common denominator. Well, let me put the second term in a common denominator first. I multiply everything by 4, and then I divide by 4. Now notice that it's n plus 1 squared, and this is just n plus 2 squared over 4. Oh, I noticed that Pn plus 1, this is the right-hand side of Pn plus 1. So Pn plus 1 is true. Hence, Pn is true for all n. So hence 1 cubed plus 2 cubed plus n cubed is equal to n squared times n plus 1 squared over 4 for all n and n. Now we move on to an example that is of the same difficulty, but might be slightly trickier. We'll see why. And this example states that the sum of the odd numbers from 1 up to 2n minus 1 is equal to n squared. So let me call this proposition Pn. And let me check what Pn is. So we start with the base case. P1 states that, well, 2n minus 1 if n is equal to 1, this is just 2 times 1 minus 1, which is 1, is equal to 1 squared. Well, of course, P1 is true, since 1 is equal to 1 squared. Now the induction step. So we'll assume that Pn is true. Assume that Pn is true for some n in n. We'll show that Pn plus 1 is true. Now let us write down what Pn plus 1 is. Pn plus 1, well, I mean, let's do a small example here. P1 is 1 is equal to 1 squared. P2 is, what is P2? Is 1 plus 3 is equal to 2 squared. P3 is 1 plus 3 plus 5 is equal to 3 squared. Well, what is Pn plus 1? Let's pay attention here. This is 1 plus 3 plus 5. Now remember, wherever I have an n, I need to replace it by an n plus 1. So what I'm really doing here, I'm replacing the n by n plus 1. So I still distribute the 2 for the plus 1. Then on the other side, I have n plus 1 squared. This is a very important part, not to just say that it's 2n plus 1 minus 1. This is not true. Notice that I have to replace the n by n plus 1. So the n plus 1 will also get multiplied by 2. Okay. Well, let me write this in a better way. Simplify it. 2n plus 2 minus 1, this is just 2n plus 1, is equal to n plus 1 squared. So we need to show that Pn plus 1 is true. Of course, in the same way, we'll let Pn appear. To use that Pn is true. Let's rewrite this. One plus 2 plus 2n plus 1. Now notice this, it's 1 plus 3 plus 2n plus 1, 1 plus 3 plus 5 plus until 2n plus 1. What is that equal to? Now notice the odd number before 2n plus 1 is 2n minus 1. Here, I can make use of the fact that Pn is true. Pn is true. So what is this equal to? This is equal to n squared. Now the remaining terms are 2n plus 1. Well, definitely this is equal to n plus 1 squared. Oh, this is just the right-hand side of Pn plus 1. Hence, Pn plus 1 is true. So I have proved that if Pn is true, then Pn plus 1 is true. Hence, Pn is true for all n, or it's 1 squared. It's 1 plus 3 plus 5 plus 2 to the n minus 1 is equal to n squared for all natural numbers and by induction, by the induction principle. Okay, now we'll move on to an example that is slightly more difficult, but not so much. I mean, this example I think can be done in many ways, but let's try with induction. Okay, so the statement Pn is just that 8n minus 7n minus 1 is divisible by 49. Well, let's look at the base case. What is P1? P1 is 8 minus 7 minus 1 is divisible by 49. Well, P1 is true, right? This is obviously true because 8 minus 7 minus 1 is equal to 0, which is of course divisible by 49. Okay, now we move on to the induction step. Now this is the critical step here. Suppose that Pn is true for some n. We need to show that Pn plus 1 is true. Well, we need to show now what does Pn plus 1 state? Pn plus 1, so wherever I have an n, I replace it by n plus 1. So it's 8 to the n plus 1 minus 7. The entire n plus 1 must be multiplied by 7. The whole of n plus 1 must be multiplied by 7 and not just the n is divisible by 49. Okay, so I mean, how to proceed to do that? Well, first, we just should write this. And it's very important to let Pn appear. Here, it's usually a bit trickier. So basically, we need to let 8 to the n minus 7 times n minus 1 appear. How do we do this? This is a bit tricky, but it's not very difficult. So first, let's just write this. Let's just write 8 to the n as 8 times 8 to the n, and we keep everything else the same. Now, there is a way to let this 8 to the n minus 7n minus 1 appear. If I just add, or if I just subtract minus 7n minus 1, oh well, let me just write this here. If I just subtract 7n and 1 from 8 to the n, and then add them back again, but this time multiplied by 8, because what I'm removing is 7n times 8, 1 times 8. And then minus 7n plus 1 minus 1. Let's see what I get. So I have 8. Now it's a good sign that I can use my induction hypothesis. Now let's just expand this. So I get minus 7, 8. Minus 7 minus 1 is minus 8. Plus 8 times 7 is 56n plus 8. Okay, let's see what happens. well, 56 minus 7, this is just 49n, and the 8 will cancel out. Well, really, what I really can say here is that we're done, right? I mean, if you want to be a bit more precise, 8 to the n minus 7n is divisible by 49, since Pn is true. So 8 to the n minus 7 and minus 1 is equal to 49k for some k in n. Or I mean in z, let's say. Because we don't know that this quantity is strictly positive, but I mean it's, yeah, I mean it's more or less obvious. So what we can do here, you know, I'll follow up here. This is 8 times 49k plus 49n. Now let me factor 49 out, so I get 49 times 8k plus n. This is just 8 to the n plus 1 minus 7 times n plus 1 minus 1. Hence, 8 to the n plus 1 minus 7n plus 1 minus 1 is equal to 49 times 8k plus n, which implies it is divisible by 49. Which hence implies that Pn plus 1 is true. Hence, Pn is true for all n in n. Hence, 8 to the n minus 7n minus 1 is divisible by 49 for all n in n by induction. Okay, now a small comment here. What we did in the induction hypothesis is we have added, we have factored out an 8 from 8 to the n plus 1 and added or subtracted 7n plus 1 in the brackets. Now there's another way where this could have been done. What if we just added, well, what if we just expanded first what we had? And notice that all I need to do to let an 8 to the n minus 7n minus 1 appear in the induction step is just to have added an 8 to the n here. This is correct, as long as we're not violating the rules of mathematics. Let me regroup the terms. Sorry, this is here should be plus. Now I can factor an 8 to the n out. I get 8 minus 1 minus 7. This is 8 to the n times 7 minus 7 plus 8 to the n minus 7n minus 1. Now here, this method is a bit longer, but it still leads to the correct answer, as we'll see. Now I have let that 8 to the n minus 7n minus 1 appear. Now I have to deal with this term. Of course, it's not very hard to show that this is divisible by 49, but let's make use of what we have. Now we know that Pn is true. And let's make use of induction as well. And we have written 8 to the n minus 7n minus 1 as 49k. So 8 to the n minus 1 is just 49k plus 7n. Well, this is just 7, and let's just replace a to the n minus 1 by its value in terms of k and n. So it's 49k plus 7n, and this is just 49k. Well, let's write this. This is 7 times 49k plus 49n by just expanding the 7 plus 49k. We can notice that 49 is a common factor. 49, 7k plus n plus k, which is just 49 times 8k plus n. Now notice that this expression here is the same as this expression here. And both are equal to 8 to the n plus 1 minus 7n plus 1 minus 1. This is a reassuring fact that we're getting the same thing on both sides. I mean, these two methods are independent of each other. Well, I don't want to say independent, but one can follow one or the other. But we see that both lead to the same result. So if Pn is true, the same conclusion will hold. Then Pn plus 1 is true. Okay, thank you very much. We'll follow with harder example next time.